Welcome to Fuzzy Mathematics, the Basics. In the previous lecture, we have talked about partial ordered sets, POSEs. In this lecture, we're going to talk about representing relations using diagrams. Our discussion will be confined to relations on a finite set. Each element of the set is represented by a point, and each ordered pair is represented using an arc, with its direction indicated by an arrow. We use such pictorial representations when we think of relations on a finite set as directed graphs. A directed graph consists of a set of vertices together with a set of ordered pairs called edges. The vertex A is called initial vertex of the edge, and vertex B is called the terminal vertex of the edge. An edge of the form A, A is represented using an arc from the vertex A back to itself. Such an edge is called a loop. What are the ordered pairs in the relation, represented by the directed graph shown here? A is related to A, B is related to B, C is related to C. A is related to B, A is related to C, B is related to C, C is related to B. Relation R is the set of these ordered pairs. We can represent relations on a finite set using diagrams. Next, we are going to talk about Hasse diagrams, which are used to represent partial ordered sets. Let's illustrate Hasse diagrams with an example. Example 1. A is the set with the 5 elements 1, 2, 3, 4, and 6. Show that the divisibility relation is a partial order on the set A. It is easy to see that the divisibility relation is reflexive, antisymmetric, and transitive. So it is a partial order on set A. What are the ordered pairs in this relation? The ordered pairs are 1, 1, 1, 2, 1, 3, 1, 4, 1, 6, 2, 2, 2, 4, 2, 6, 3, 3, 3, 6, 4, 4, 6, 6. The directed graph of this relation is displayed here. They are the edges of the directed graph. But many edges in this directed graph do not have to be shown because they must be present. For instance, because this relation is a partial order, it is reflexive, and its directed graph has loops at all vertices. We don't have to show these loops because they must be present. So, in the next figure, the loops are not shown. No loops. Secondly, because a partial order is transitive, we do not have to show those edges that must be present because of transitivity. For example, there are edges 1, 2, and 2, 4, so the edge 1, 4 must be present. And there are edges 1, 2, and 2, 6, so the edge 1, 6 must be present. In the next figure, the edges 1, 4, and 1, 6 are not shown because they must be present. Remove all the edges must be present in the poset because of the presence of other edges and transitivity. In this figure, the third edges are not shown. No, the third edges. Now, there are 5 edges left. What are they? 1, 2, 1, 3, 2, 4, 2, 6, 3, 6. Finally, we assume that all the edges are pointed upward, as they are drawn in this figure. All edges are pointed upward. We do not have to show the directions of the edges. No arrows. All edges are pointed upward. 1, 2, 1, 3, 2, 4, 2, 6, 3, 6. This is the Hasse diagram of this postage. No loops, no sharp edges, no arrows. In general, we can represent a finite postage using this procedure. Start with the directed graph for this relation. Firstly, a partial order is reflexive. A loop XX is present at every vertex. Remove these loops. Secondly, remove all edges that must be in the postage because of the presence of other edges and transitivity. That is, remove all edges x, z, for which there is an element y, such that x is related to y and y is related to z. Finally, arrange every edge such that its initial vertex is below its terminal vertex. Remove all the arrows on the directed edges, because all edges point upward toward their terminal vertex. These steps are well defined, and only a finite number of steps need to be carried out for a finite postage. When all the steps have been taken, the resulting diagram contains sufficient information to find the partial order, and it is called the Hasse diagram of the postage, named after the mathematician Hermann Hasse, who made extensive use of them. Another example, example 2, show that the less than or equal to relation is a partial order on the set A. A is the set with the 4 elements, 1, 2, 3, 4. It is easy to see that the less than or equal to relation is reflexive, antisymmetric, and transitive. It is a partial order on the set A. What are the ordered pairs in this relation? 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, 4, 4. The direct graph for this relation is displayed here. Next, find the Hasse diagram of this postage. Firstly, remove these loops. Because this relation is a partial order, it is reflexive, and its direct graph has loops at all vertices. We do not have to show these loops because they must be present. In the next figure, these loops are not shown. Secondly, remove all edges that must be in the partial order because of the presence of other edges or transitivity. For example, 1 is less than or equal to 2, 2 is less than or equal to 3, so 1 is less than or equal to 3. In the next figure, the edges 1, 3, 1, 4, and 2, 4 are not shown because they must be present. Finally, we assume that all edges are pointed upward, as they are drawn in this figure. We do not have to show the directions on the edges, because all edges point upward toward their terminal vertex. Remove all the arrows on the directed edges. And this is the Hasse diagram of this postage. It is easy to see that every 2 elements in this postage are comparable, so set A is a totally ordered set. Maybe that's the reason why a totally ordered set is also called a linear ordered set or a chain. In this lecture, we have talked about Hasse diagrams. which are used to represent poses on a finite set. Next time, we are going to talk about elements of poses that have certain extremal properties. Thank you.